probability that nature selects HIV positive for this person? 1%. Okay, so 0.01 there, 0.99 there. If they're actually positive, then the test will come up positive with probability 0.99, and it will come up negative 0.01, and vice versa if the person is actually negative. Okay. Now, what we want to know is, so here's an outcome where the person actually is a HIV. Sorry, here's an outcome where the person gets tested positive. Here's another outcome where they get tested positive. What we want to know is, of the times when they test positive, how many of those times were they actually positive? So what is the probability of this outcome as a subset of the probability of either of these outcomes together? Okay, or the ratio of those two things. So here we have the outcome here is the probability that we would observe a signal test positive, given that, right, conditional on, the pipe is sort of conditional on, or given that, the state of the world, the hypothesis, or sorry, yeah, the state of the world is that they're HIV positive, and it is probability given. So sorry, this object here is the probability that the test is positive, given that they actually are HIV positive. This is the base rate probability that they're HIV positive, and what we get is that the probability that they are HIV positive and that they test HIV positive, right, is equal to this probability times this probability, right? So it's how likely are you to be HIV positive, how likely are you to be have a positive test if you are HIV positive. You multiply those two things together, and you get 0.99 times 0.01, which is 0.0091, I think. Is that right? 99. Yeah. Okay. Here, okay, this object here, right, is the probability that you will test positive if you are in fact HIV negative. That is 0.01, not super likely. But in order to get the probability that you are HIV negative and right, so this comma says and also test positive, is we take this conditional probability that you would have gotten a positive test if you were negative and multiply it by the base rate probability that you were negative in the first place, which is 0.99. Right? And so there we are, 0.0099. Okay? So there are two situations in which you could have wound up with a positive test. One is that you were positive and got it correct. This is like a true positive, this is a false positive. Turns out they're equally likely. Okay? So the probability, if you see a positive test, that it was from an actual positive individual is 0.5. Okay? The test is seemingly extremely accurate, but in terms of how accurate the information is that it generates for you, it's hopeless. Right? Does that make sense? No. Why does that not make sense? Your name is Yvonne? No. What? Olivia, sorry. I have the two of your names mixed up. What was your question? Okay, fine. You looked like you had a question mark on your forehead. Now, a whole bunch of you, some of you said 0.5, and some of you said some number between, some of you said 0.99, and some of you said somewhere between 0.5 and 0.99. My question to you is, for those of you, and your answers are the same as everybody else's answers. Most people instinctively say 0.99 or somewhere between, something too high. Okay. So the question is, what do you think people are getting wrong? What do you think you guys are getting wrong when you do this in your intuitive? I didn't give you long enough to write this thing down. Okay. I will get people who come up to me and they show me their notes and they've done all of this in the space of about 20 seconds. Those people are going to get a high GRE score and move on to make tons of money. The rest of us have to puzzle over the answer to this question. What do you think people are getting wrong in the HIV test example? Are they ignoring the fact that the accuracy of the test is the same for positive and negative outcomes, right? So the accuracy is 0.99 if you're negative, 0.99 if you're positive. Are they ignoring the fact that there's more than one way to get a positive test result? Like, oh, it didn't even occur to me that actually you could get a test result if you're negative. Are they ignoring the fact that HIV is very rare in the population? Or are they just guessing wildly? We know they're not guessing wildly, right? Because wildly, if by wildly we mean completely randomly, we would have expected some people to think it was less than 0.5. Of course, I didn't give you that option, but what do folks think? What's anybody's guess as to what's really going wrong here? Yeah, Alex. You think people do all of them? Suppose that I was an editor of a journal and you were submitting a paper in which you said A, B, and C, and I said, I'm sorry, that's not a contribution to literature, you need to pick one. Ignoring the fact that there's more than one way to get a positive test result. And just on the basis of introspection, those of you who said something other than 0.5. Does Alex's answer of B, like, oh, that's right, I forgot. Does that resonate? Sorry? How to compensate for the fact. So you were like, oh, yeah, I see what the problem is. The problem is they could come up positive, but that's super unlikely, right? Right, exactly. You're like, I learned Bayes' rule in 5th grade, I can't remember. The thing that's, so if you remember this, and then you're like, oh yeah, but this thing's really, that doesn't happen very often. That only happens 1% of the time. The reason, the shocker here, right, is because it's actually just, that's what's actually most likely. So yeah, this is only 1% of the time that people are negative, but people are negative almost all the time. Okay? So that is an answer of C, ignoring the fact that HIV is very rare in the population. Okay? Now, going back to what I was saying a minute ago about, I said a minute ago about HIV. You grab a patient off the streets, right? People who are trying to eliminate HIV, they drive around in vans with HIV little testing things going on in the van, and they drive around to hotspots where they think that MSM, men who have sex with men, are lurking, and they try to entice them to come into the van and get tested. So you're grabbing some random member of the population. All you know about them initially is that there's a 1% chance that they have HIV, right? Unless you think that the length of their beard tells you something about it. So all you know initially is this, which we call the base rate, okay? And then you give them a test, and it comes up positive. And one sort of hypothesis or theory as to what happens is that people just go, and they just look at that, okay? And they might be looking at this too, like Andrew said. I know I'm supposed to care about that, but I forget how much I'm supposed to care about it. And how much you're supposed to care about it is this. You're supposed to care about it a lot in this situation, because it's the most likely baseline state of the world. So we have this idea that in lots of situations, people, I said base rate length, don't write one word when you're saying another. Base rate neglect is what I meant to say. We have this idea that people suffer from base rate neglect in lots and lots of situations, okay? And this is a classic situation, and lots of people get this wrong, and in particular lots of doctors get it wrong. And any of these could also be correct answers. But this is one we're going to care about a lot. Okay, so now let's actually pick apart Bayes' rule in detail. Okay, so when we're talking about probability inference, the object that we are interested in is always going to be the probability that some hypothesis is true given some signal that we see, the probability of H given I, right? So that notation you're going to see a lot. In this case, the hypothesis is that you're HIV positive, the signal is that you have a positive test. And the way we're supposed to compute that probability is to take the probability that we would have seen, the probability that we would pull someone out of the population who's HIV positive. Sorry. So this is what's called a joint probability, the probability of H and I being true at the same time. So the way to think about that is, I pull someone off the streets. What is the probability that they are HIV positive and will come up with an HIV positive test result, right? And that was this joint probability. What's the probability that you're HIV positive and get a positive test result? It's this. And that comma, when we notate it that way, says this is a joint probability. It's the probability of two things happening jointly at the same time. Okay, and it's just the product if they're independent from one another. They're independent from one another. Yes, if they're independent from one another, it's just the product of their probabilities. And then you divide that by the total probability that you would have seen the signal in any situation, right? So what is the probability that you would see any HIV positive test result? Well, there's a 0.099 probability that you would see it from a positive patient, and there's a 0.0099 probability chance that you would have seen it from a negative patient. So out of the entire population, there's a somebody. What is you add those together and you get 0.0198? Is that right? Yes. So probability in this case, the joint probability of someone being positive and showing up and getting a positive test result is 0.0099. The probability that any randomly selected person off the streets would have tested negative is the combined probability that would have happened and they were positive and that it would have happened and they're negative, which is 0.0099 times 2, 0.0198, right? And so the actual, the probability of the hypothesis being true, given that the signal is true, is the ratio of those two things, which in this case is 0.5. Okay? That's the math. First you figure out the joint probability of the hypothesis and the signal happening at the same time, and it's the same case, and then you figure out what's the sort of combined probability of seeing the signal given all of the different ways that we could have seen it. We could have seen it from a positive person, we could have seen it from a negative person, sum that up, and you take the ratio. Okay? Okay, so there's that written out. Now, where does this come from? So this was Bayes' contribution. It's quite simplistic. Well, Bayes had lots of other contributions to make. Yeah, so I'll do it here. So what Bayes said was, he said, look, we know by definition that the joint probability that thing A is true and also thing B is true is the probability that thing A is true multiplied by the probability that thing B is true when thing A is true, right? So for thing A and B to be true at the same time, it first has to be true that thing A is true, and then it has to be the case that this is a situation where thing B is true given that thing A is true. I know that doesn't quite make sense, but it will in a second. So let's let A, so this is going to be a universe of weather. This is going to be the universe of weather, and I'm going to give you a climatological example that is appropriate for today. Suppose that A is the state of the world in which the weather is cold, okay? And suppose that B is the state of the world in which the weather is rainy. Now, sometimes it's cold and rainy, sometimes it's cold and not rainy, vice versa. Sometimes it's rainy and not cold, sometimes it's rainy and cold, right? So these are intersecting events, okay? So, and sometimes it's right, sometimes it's neither of those things. Sometimes it's hot and dry. So we could imagine in the universe of all possible weather states that there's a set A, which is all of the days when it's cold, okay? So this is the set of cold days. I'm just going to call it cold, okay? And there's another set of days when it's rainy, okay? So this is an event. This is another event. And what we want to know is the size of the set, or the probability that a day is cold and rainy. Okay? That's this joint probability. Okay? How do we get that? Well, the size of this circle is the probability the day is going to be cold, right? And the size of, then what we want to know is what's the probability that that day is also rainy. Okay? So this area here, sorry, am I about to do this wrong? Probability, I am doing this tick, 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 tick. I'm rebooting my hard drive. Okay, all right. So what we're doing here is we're saying we want to know, so the universe of all weather, right? We're thinking of the area of the set as being representative of the probability. So the area of the entire universe is 1, right? There's a 100% probability that there will be weather, right? So the size of this circle is the probability that any given day will be cold. And what we want to know is what is the probability that it will be cold and rainy. That's the thing we're starting out with here in the derivation of Bayes' rule. And what it is it's the probability that it's the probability that the day is cold multiplied by the probability that it's cold, that it's rainy given that it's cold, okay? This set here is the probability that it's rainy and cold, which is this thing. And so what we need in order for it to be rainy and cold is we need it to be cold, and then we need to know the probability that a cold day will also be rainy, which is this conditional probability. Okay? What Bayes' rule does is it flips this on its head, and it says, okay, suppose all that you observe is the temperature, right? So suppose you're not able to see outside, but someone says, boy, it's cold outside. And what you want to do is you want to say, all right, given that I know it's cold, what's the probability that it's raining? Because I've got to decide whether or not to bring my umbrella. That's this thing. I want to know what's my best guess as to the probability, what is my inference of the probability that it's going to be raining outside given that it's cold, right? So the area of this thing is the probability that it's rainy and cold. What I want to know is what's that area as a proportion of the event it's cold, right? So this is a situation where I know it's cold, so I can narrow my universe down to this. And what I want to know is what proportion of the probability, what proportion of that event, what proportion of the times that it's cold is it also rainy? Okay, so it's this thing. I'm going to call that area 2, as a proportion of this thing, which I'm going to call area 1. Okay, so obviously Bayes' rule just says, well, this thing is that thing divided by this thing, right? So the probability that it is rainy, given that it's cold, is simply equal to the probability that it is rainy and cold, right? That's the size of area 2, divided by the probability that it was cold in the first place. Right? So that is equal to area 2 divided by area 1. Right? Yes? I totally get what you're asking, and you've just made it clear to me that I did not draw this diagram in the most informative way. So let's try it this way. It's cold a lot of the time. It's not raining that much of the time. Okay? Sorry, let me do this. It's not raining that much of the time, but most of the times that it's rainy, it is cold. Wait, where's my interlocutor? Who asked the question? There we go. Okay, so it's cold a lot of the time, but it's not rainy that much. But when it is rainy, it's highly likely that it's going to be cold. Okay, so this is the joint probability that it's rainy and cold. It happens a decent amount of the time. It's much more common for it to just be plain old cold, rainy or otherwise, which means that the conditional probability that it's rainy, given that we already know it's cold, is pretty small. But if we already know that it's rainy, and we're just trying to guess whether it's cold or not, well, as a proportion of the proportion of the days when it's rainy that it's cold, right? The proportion of days of rainy days that are also cold is very high. Okay, so the conditional probability of it being rainy, given that we know it's cold, is this area divided by this big thing. The conditional probability that it's rainy, given that we see a signal of that it's cold, given that we see a signal, is that same joint probability as a proportion of the probability that it was rainy in the first place. Okay? The joint probability is always the same. You can go and look at a distribution of weather historically and say, here's the percentage of days when it is rainy and cold. Yeah. Okay. So this is my rainy days, cold days explanation of how Bayes' rule is supposed to work. This is how it's derived. This is the definition of joint probability mathematically. And then you back out of that the formula for the probability of the hypothesis it's rainy given the signal that it's cold. And it's this. And it's always the same. It's always this. It's the joint probability of the hypothesis and signal happening at the same time divided by the unconditional probability of seeing the signal under any conditions. So, so this big circle was area 1, and this football shape was area 2. Okay, so it's this thing. So essentially what you're doing is you're saying, look, we were going and saying, the probability that it's cold. This is a graphical model in which the area of this rectangle is 1. So the ratio of the area of, right, so this is the circle of cold days you could think of as, this is the intersection of the set of days that are cold with the set of days that are days. Right? So its probability is this thing divided by 1. This is a subset of those days we're interested in. We already know that it's cold. So essentially what we're doing is normalizing the universe. But this is a situation we already know it's cold. So we're sort of normalizing and saying, what if we treated the area of this circle as 1? Okay? Then what would be the probability of this if we start with this cold days as the universal set that has probability 1? Because we already know it's cold. And you do that normalization by simply dividing by the probability that it's cold. That's another way of thinking of it. Right? So if you want to know the probability that how likely it is that it's rainy and cold, given that it's just any day, randomly selected day, it's that area divided. It's the probability of that divided by the probability of it being a day, which is 1. And if you want to know what the probability is, given that we've already narrowed the universal set to just cold days, you normalize the sort of you normalize the probability by saying we're just going to treat we're going to say that it's with probability 1 it's a cold day, so we're going to normalize this area to what proportion is it of that area. Okay. Every year that I've taught this material, I've found the same exact thing happens, which is that I say it about 17 different ways, confuse myself thoroughly, and 1/17 of the class gets it each of the 17 ways I say it. Oh, I'm sorry. I shouldn't have used numbers. Let's call this area, x, and let's call that area y. Okay, so it's y over x. Yeah, thanks. Sorry, that was unfortunate notation. Okay. Next. Okay, so that's Bayes' rule. What I'm going to do now is I'm going to drag you through. Okay, so this is a sort of spatial model, if you want, that's not at all rigorous. So now what I'm going to do is I'm going to take a different situation, a little bit more complicated, which is the mutual fund manager situation, and I'm going to use the same spatial approach, but I'm going to do it in a more rigorous way. And I claim, I've been wrong about similar claims in the past, but I claim that this way of thinking about and even computing Bayes' rule is actually a useful tool.